Hi everyone, thanks for taking the time to come here. So today I'm going to be talking about how we can bridge data and models for optimal control of robots, and kind of just show you what the world of robotics is, broadly. So as the wonderful introduction, I'm a PhD student at Carnegie Mellon University, Robotics Institute. I'm advised by Professor Chris Atkinson, who's done a bunch of cool robot stuff. I studied at Lowell College of Engineering. If you ever want to come find me, this is Carnegie Mellon. Zoom in, my office is right there. You can come bug me at any time. Here's a bunch of random robots and projects that I've worked on. I have some experience across a bunch of different robotic domains, and like ground robots, land systems, computer vision, software robots, manipulators, drones, different types of systems. So if you have any questions about any of those things, feel free to come ask me at any time. So I'm going to start with just a short story. Kind of how I got into the current research direction and area that I'm working in. Also, really quick, is my English accent good? Understandable? No, it's okay. I'm really pissed on English like it's fine. Okay. I'm not. Okay. So I'm going to start with just a short story. When I kind of started robotics, my overall conception and idea of what a robot can do was really in this left area. So you see like these factory robots and some manufacturing plant, they pick up a car, weld things together. And it was also something like this like Honda Azima robot, where it would very slowly take a step and then move. And most of these really relied on these pre-programmed instructions. At the time, some of the robots I was building, they like pick blocks up and move them around, and they really relied on these highly engineered, designed, pre-programmed type of instructions. And after kind of doing a lot of this, in about 10th grade, I saw this video, and it kind of blew my mind, because I saw this and I was like, how in the world, as a robotics engineer, would I pre-program a robot to do that? Every single joint, every single actuation, taking sensor data and computing trajectories for this robot is an incredibly hard challenge. So I was really confused. How did they do this? And if we skip forward to today, robots are doing even more incredible things. So this is a robot video from a couple days ago. It's from a company called Industry. That robot's doing, I don't think I can do any of that. So it's really incredible things that it's doing. Robots, this is a drone robot from Switzerland. It's flying through those hoops right there. And it's actually faster than any human on Earth at controlling the drones that fly through those hoops. There's like a drone racing competition. There's also like other types of mobility vehicles. So there's like a bicycle and it can do jumps and stuff. This is a robot dog with wheels on it. And you can drive around, do crazy flips like that. So the question is like, how in the world has robots improved so quickly? Even still, that's not really interacting with the environment that much. That's kind of just on its own doing crazy things. But we're starting to see in like forefront of research that robots are able to do really incredible, intelligent behaviors that are very useful and starting to kind of leave the lab. So this is a robot dog. It's able to take some tires, roll them around, stack them. This is a bimanual robot setup. It's able to grasp an apple, core the apple, cut stuff. So, robots have really accelerated in growth. And robots are actually starting to become very useful. This is a Waymo self-driving car. Right now in San Francisco, they are doing 1 million rides per month, autonomously, fully autonomously, no driver behind the wheels. And similar to that, this is a drone delivery robot. So this guy can put a package in this holder piece. He goes up, lifts into a drone, and it flies to your house, and then drops the package right in front of your doorstep. And on my way here at the London airport, I ran into this robot. It was cleaning the halls, electrifying the ground, and I was impressed that robots were just appearing in our daily lives. And overall, I would say it's probably one of the best times to be working in robotics. There's so much money coming into the field, and there's so much new innovation that's coming along. And back to the original question, how have robots improved so quickly?
Wait.
There's three main areas that I would say that robots have kind of grown in. First is the algorithms. Algorithms have improved in different ways. The hardware itself has grown. And the actual computational resources that are available. Like you've heard of, how many of you guys have heard of ChatGPT? ChatGPT?
Yes.
How bad is that? The amount of compute that's required to do something like that is incredible, right? And those resources are available to robots now too, so we can do much more amazing things. And I would a little bit split up what the kind of progression of robotics has been slightly differently. So from this original kind of very slow, methodically walking robot to the robot that can do backflips and cartwheels and stuff, it's actually more so just an algorithmic improvement. There was much more embracing of certain algorithmic techniques that have really improved things. But from that video to the last video, it's mostly just compute. I would argue that it's mostly a computational scaling of the amount of resources that we're able to allocate to these algorithms that we have. And all the while, hardware has been improving, but hardware generally improves much slower. Unfortunately, I can't really tell you how to improve the compute, because it's more so just buy more compute or buy more GPUs. There's intelligent ways to use the compute you have, but that's not really the point of the talk today. In terms of hardware, I would say there's incredible innovations that are slowly happening. It's a much more slower progression, because it's not really like you do something and then it solves all the problems. It's more so gradual, iterative process of improving hardware. And that's where you guys come in, and improving the hardware. But today I'm going to talk a little bit about the algorithms, because it really connects to a lot of the theory and more mechanical engineering subjects that you've learned, but in a slightly different perspective. So the core idea of the talk today is going to be about optimization. This is like the core crown jewel that most of the algorithmic improvements have came from. Most of the current algorithmic techniques really embrace optimization. Like this robot doing a backflip, you don't need to program the exact joint angles and leg muscles and torques. You just need to ask the robot, do a backflip, and then give it some additional information, and it'll automatically figure out how to do the backflip. Right? If you have to leave early, I have the conclusion at the beginning. The core idea is really that optimization is a critical and powerful tool for robotics. It's one takeaway. You'll see optimization in a bunch of different landscapes and views, but I think as a general purpose framework, thinking about these problems, it's fantastic. And critically, always should keep in mind that all models are wrong. Everything you learn in mechanical engineering, in some degree, is going to be wrong. But they're all incredibly useful tools, and keeping in that duality of what is useful and what is wrong is really important. Okay, so we're to the real material today. I'm going to start with a little bit of an optimization background, show you just a little bit of math, not too much to scare you, hopefully, and then we'll do a little bit of linear systems theory, very briefly, and then we're going to talk about what's called the linear quadratic regulator. It's like the crown jewel of robotics control. It kind of ties in a lot of these ideas. We're not going to do the full derivation. We're going to go just a high level, and then we'll do an interactive demo. Do you guys all have phones or laptops or any good likes? Phones? Phones? Okay, phones, great. It'll show down there. And then we'll talk a little bit about what are all the drawbacks, limitations, and how we can better solve these problems. Okay, a couple of rules. I'm going to be asking lots of questions. Within 5 seconds, can I get a promise that somebody will raise their hand? I don't care if you're wrong. Somebody should just raise their hand immediately, okay? Yes? What do you think? That's it. Okay? Okay, great. And if anything is confusing, please ask me. Because if it's confusing to you, it's probably also confusing to everywhere around you as well, right? So please ask me. I will answer it. If anything I say doesn't make any sense, I talk a little bit fast. So feel free to tell me. I'll repeat it. I'll try to translate summary as well. I'll say. How's everybody feeling? Ready?
Yes.
Sounds good? No? Okay, fantastic.
It's pretty good. That's it.
Okay, so let's start with optimization. How many of you folks have heard of optimization before? Right?
Okay.
Nobody. That's fantastic. So we got some new materials. So let's start with just a simple example of what is an optimization problem. Let's say you're in Kudonlai, right? And you're at the Kudonlai bus stand, and you want to go to the temple. There's a bunch of different ways you can actually get to the temple, right? You can go on the main road, you can take Kukmurli, right? There's a bunch of different ways you can get there. But you, as a person walking from those two places, probably want to minimize the amount of energy, the amount of walking that you're doing, right? You want to take the shortest path, or the least kind of active path. So you might potentially take this path. It might take you a little bit longer, but you can clearly see there's a shorter path, right? You can go straight this way into the alley. Or you can take a scenic route, go right and come back, that's it, right? A bunch of different ways you can do the same problem, but each of these have a different energy cost, right? It takes you more energy to go up the mountain and come back down than it does to just go straight there. So in optimization, the goal is to effectively minimize whatever this energy is. So we'll define this cost function, f of x, which takes in the path. So whatever path you're going in is that x variable. And the output of that function is the energy it takes. Does that make sense?
That's good.
Start place to the recommend the English deliverable here. After this area.
Yes.
Yes.
So the question is, how can we find the minimum value of this function, right? What is the lowest amount of energy it'll take to get to wherever we want to go, to solve whatever problem we want to do, and we need to make a decision on what path to take, right? Does that make sense? And this function right here, that f of x, oh, sorry, that doesn't show that well, but that's called the cost function. I'll refer to it as the cost function. This is how much cost you need to pay in order to do something, right? So it's sort of a simple example. This is the function, f of x equals x squared, right? Quadratic function. Hopefully you've seen quadratic functions somewhere in public. And it kind of looks like this, like a bowl, right? Can somebody tell me where's the minimum of this function?
I was
No? Where's the minimum of this function?
definition just stopping being
Is it here?
I should do it about
Where's the lowest point of this function? Right
center
here.
point.
Right at 0. And effectively, we know that that's higher. So if we look for this was your favorite. What was your favorite robot video of the videos? Who do you know? And the robot alone function, right? Adile உங்களுக்கு ரொம்ப பிடிச்ச robot humanoid. கரெக்ட். சரி. உங்களுக்கு
So like your doggy is right.
எந்த
It's a
நாய்
dog
மாதிரி
also.
இது. Oh, it's just Oh, and this Okay. Can I get everyone's step? Ready? Okay, let's go. So where are we at? So we were trying to minimize this function here, x squared, right? You said that the minimum is right there, right at the bottom. And I agree with you. Yes, the minimum is right there. And I have a question. How did you know that the minimum was there? Yeah, it's the lowest point, right? You wait, what is it? The slope? The slope? Yeah, the slope right there. ஒரு பந்து அங்க மேல போட்டீங்கன்னா கீழே வந்து அங்கதான் நீங்க இருக்கும் சரி. The algorithm that you guys just did in your head is called fixed point iteration. You started at some higher place, and then you went lower, 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 and then you eventually got to the right position, and then you tried going more, and it was higher, so then you know that's the right point. You can also take the derivative of that function. So x squared, the derivative is 2x, right? And you know that right at that point, the derivative is going to be 0, because it's flat. Right? Because on this side, the derivative is positive, and then on this side, it's negative. So somewhere it needs to cross 0, right? So right at that point where it crosses 0 is the minimum. So since 2x equals 0, we know that x must equal 0. That's all. Okay, now we have a new function. f of x equals x. It's just a line.
So, is that
What happens when we minimize this function?
You see with the magnitudes.
5, 4, 3, 2, 1. Nobody raised their hand. I don't know.
You're adding that.
Okay, I'm gonna do a new thing. If nobody, I'm gonna hold my breath, and if nobody raises their hand, might get you in the setting law.
Sen jag kan tänka att ibland då vi vet att det är bra men det ser man innan det är det så vi kan då det så tack så igen
Sat down still. Is
Thank you.
it straight like true ones?
Enger på.
It's up to down sides.
Oh,
Center of
here.
axis. Yes.
Put in one. It'll actually slide all the way, start up here, slide all the way down. It'll actually go down to negative infinity, right? There's nothing stopping it, right? You just minimize all the way down. That's not that useful, right? Like, you know, thank you, you're probably going to say minimum of this function is negative infinity. So, what if instead we add some bounds? Oh, perfect. Imagine if it was there's actually like a line here. And you're going to that's called a constraint. So we're constraining what the allowable region of x's are. I'll just show you. So you see how there's like a green area here? That green area? That's like a constrained region. So we're only allowed to choose values in that region. So when we minimize this function, we start at the top of that green region, and then it'll go down and only be limited by the constraint. Does that make sense? Okay. So in general, writing this optimization problem down that we just did in this form is very common. It's kind of what if you ever Google anything, where this value right here, that's called the decision variable. It's the variable that we get to choose when we're trying to solve this problem. And this is, remember, the cost function that I was saying earlier. And these are the constraints. So those are the things that we need to satisfy and define what is allowable. So in general, this kind of looks like this one. There's like minimum over x of some cost function subject to some constraints. Make sense? Doesn't make sense? Okay. Mostly makes sense. And I would say this framework right here is extremely powerful. Everywhere in robotics, mechanical engineering, electrical, any engineering, any sciences, optimization is a critical tool. And in robotics, you might be asking, how in the world are you going to be using this for any purpose? Right? In robotics, often what we'll do is we'll do minimum over some control actions. So we want, let's say, some joint to move in some way, and we have to have control over it. That's what our decision variable is. Our cost function will be the system error. So let's say we want the robot to go from like here to here, but it actually goes over here. That would have a higher cost than if it went to the right place. Does that make sense? And then the constraints can be something like the dynamics constraints. So let's say I'm walking, robot's walking. In those dynamics constraints, I can write things down like, don't step on the other foot. Don't hit the feet together, right? I can have these kind of allowable things that kind of stop things that we don't want to happen from happening.
Right.
Okay. Any questions? No questions?
That's
Okay. Next time I ask a question, I'm gonna hold my breath. If nobody answers, I'm gonna faint, and you'll be responsible. Okay.
yeah, I'm outside school.
How are we doing?
System.
So next thing we're going to talk about is called linear systems. So right here, and Kuchi. So as a human, I can take this pole and I can balance it, right? You know, it might take some effort, right? But how am I able to do that? You know, I'm able to know when to move right, when to move left, right? Any of you can do that. If I hand this to you, right? You can do that. So let's try to figure that out.
What is this?
So this right here is called an inverted pendulum, a cart pole.
I guess there is a lot.
So there's a cart on the top that slides back and forth, and there's a pendulum which can swing in any direction. Make sense? And usually the goal is just moving the hand on the bottom. Can you balance the pole on the top? Make sense? And this robot has a bunch of different things. It has, just a power supply down here, motor driver. There's a gearbox and connected to a motor. There's an encoder up there to track the angle. There's a belt. That's good. And all these things are really important to the actual system dynamics, right? If your belt stretches, that has huge impacts on your dynamics, right? In mechanical engineering, you're very familiar with all these different problems like stress, strain, the dynamics, the rigid body dynamics. All these things are super important. But for now, we're going to simplify a little bit and just model it as a rigid body dynamics system. So this is just like from the front view, this bottom part is a cart. You can move side to side. And this top part is a pendulum that can spin. And as the robot, it has a control over that cart on the bottom. So you can apply forces to the right and to the left. Does that make sense? So this is, remember, this is an approximation of the real system. And we're just going to stick with this for now. Maybe come back to the first time. And for the system, there's 4 quantities that are important in trying to capture all of the information you need to know about what is going on. So this is called the state. If you have a ball and you just know its position, you actually don't know everything about it, right? It could be traveling at 10,000 miles an hour, but it's just looks like it's just standing there. So you need to know the velocity and the position of each of the quantities. So for our system, we need to know the position of the cart, the angle of the pendulum, the angular velocity of the pendulum, how fast it's spinning, and then how fast the bottom is moving. Right. So if you know those 4 things, then we know the state of the system. And then we also have a control. So I can apply some force to move this way or to move this way. And how many of you guys have seen this? Okay, great. This is starting point for a lot of things. But remember, this is only a model of how the world works. This is not actually how the world works. We're only kind of representing the important aspects that we think are critical to our problem. So I'll skip a little bit of this stuff, but if you do maybe like an intro physics class in your dynamics class, you'll learn if you take the state of the system and some control, you can kind of predict what's going to happen next, right? All the forces, all of the velocities, with the information you can predict what's going to happen in the next time step. So at x, with t equals 1, if you apply some control this way, you know that the next step is going to be like this, right? And if you apply some control this way, you know it's going to be like this. Okay. Unfortunately, this function is what's called nonlinear. Anybody have any ideas why it's nonlinear? Okay, I'll count to 5. Okay. Short answer, it's because of trigonometry. In this setup, the angle is applied through sine or cosine, some trigonometric function. And that's a curvy function, right? It's not a straight function. That makes sense. That's squiggles. And that's nonlinear. And I'll show you kind of what that actually means. A linear mapping kind of looks like this, where let's say you have some grid of lines. It's, let's say, like in Cartesian, like x, y, you have a grid of lines. If you apply a linear function, all of the lines will stay parallel, right? It'll just stretch and squish and scale things, but it's never going to make it curvy. Unfortunately, with a nonlinear function, that's not true. So at each point, it does something different. You can curve it this way, curve it that way, do various types of things. And effectively, this makes a lot of downstream things we want to do really difficult. So let's try to linearize this function. Take the nonlinear function, make it linear. So if we pick some point right there, and we say, I want to be linear about that region. So when I zoom into that point, doesn't it look kind of like a grid? It looks more straight lines, right? So in the region right around that point, it's actually approximated as linear. So this was our original function. Let's do this linearization thing I just talked about, pick some point and linearize it, and now it'll look like this. Don't worry about the math, doesn't matter at all. But this is a core idea of linearization, really important. And in our case, what did we want to do with this? What did we want to do? Did we want it to fall? No. We wanted to balance, right?
Yes.
So where do we want it to balance about? We wanted to balance about vertical. So we want the approximation of our model to be accurate in this region, right around here. So let's linearize it right about vertical. And we'll know that when we predict stuff, it'll be correct around this region, right? Does that make sense? Yes, David. And these A and B are matrices. They don't really matter that much, but that's just how the dynamics evolves. So even that state, which is like 4 numbers, it's like a vector. If you multiply by this A matrix, and you multiply the control by that B matrix, you can predict what's going to happen at the next time step. Make sense? Okay. How's everybody feeling? That's almost done with the math. We can do some fun skipping. Maybe? Yes? No? Any questions? Any questions? Anytime you say no questions, I'll be sad. Just ask us a question. It's like, no, make you sad. Okay, so our goal was to balance this pendulum upright.
Right.
How do we do this? I just gave you 2 tools. One, that you can ask some question, how do we solve this problem, specify some constraints, and it'll give you a solution. Another is a way to represent the real system in some abstract, some model. Right? I would say you don't need any of it what I said to control the system. If you have a fast enough computer, you can actually just have a really simple control policy where if it's too far this way, you move this way. If it's too far this way, you move this way. And it doesn't even need to be like proportional. It could just be on-off. Like on when you're this way, and on this way. Left when you're done bent like this, and right when you're bent like this. That's called bang-bang control. That's the simplest, easiest way to control the system, and it often actually works pretty well, surprisingly. But you need a really high refresh rate, and it doesn't generalize super well to new systems. So, I'll kind of speed run through this, but this is our state of the system, remember. Position, velocity, angle, angular velocity, right? We can also create this matrix, Q, which we'll call the cost matrix, where there's zeros everywhere except for on the diagonal, like Q1, Q2, Q3, Q4. And we kind of think of this as the prioritization, like the weight that we're giving to error in the corresponding state. So if we only care about the cart's position, everything will be 0 except for Q1. If we only care about the angle, which is in our case what we do, we only care about balancing, then the Q2 is the only one that really needs to be positive. Everything else can just be 0. Kind of makes sense a little bit? Okay. And the way that we represent this in our cost as a cost function is we take the state and we multiply it by this Q and we multiply the state again. That's kind of like squaring each of the values and weighting it by the Q1, Q2, Q3. So when you see this form right here, it's very similar to like that quadratic, this like bowl. So whenever you see that thing right there, just think of the bowl. And we want to get to the bottom of the bowl.
Perfect.
And in reality, it's actually like multi-dimensional, high-dimensional bowl. It's a 4-dimensional bowl. But yeah, we can have this picture of a 2D bowl, a 3D bowl in our center. So, what is the actual optimization problem we want to solve? Let's start with the decision variable. We can control the force this way, force that way. Our cost function is this x squared qx thing, right? You know, just imagine the bowl. We also want to add a little bit of cost to our control, because we don't want to say like, you know, move infinitely fast this way, move infinitely fast this way, you might break your robot, or you know, your robot actually can't do it. Right. And then let's use that model that we just came up with, that linear model. We want to say that when you apply a control, the prediction of that control is going to be defined by that A and B linearization. And critically, this is actually also like infinite time. It doesn't matter at all. really important part here, that bottom part is linear, right? Like all the lines are parallel. And that makes it, that plus that top part being that bowl quadratic, makes it so this optimization problem is really easy to solve. You can solve it extremely quickly, and that's not generally true. The actual way you solve this problem, you can Google it. It's called like the Riccati recursive solution. Don't worry about it. It's a long derivation. It's very interesting. Does not matter at all for what you're doing. But you eventually, these equations, you solve them, and you get this bottom part. That's the only part that really matters. You get that K matrix. That K matrix that takes whatever your state is, your position, your velocity, and it maps it to the control that you need to apply. So that's kind of like what your brain is doing. Your brain is mapping the state that you see, the system, to the control that you're applying. Does that make sense? Maybe? No? You have a question? Stop. Any questions?
No questions?
Okay.
Shopping.
This is also called a policy, by the way, this K matrix. But yeah, let's see. Okay, let's try a demo. If you can all pull out your phones. Do you have your phones?
Yes, sir. Yes, sir.
Okay, can you take your phones out?
And I was
So you should be able to connect to my Wi-Fi that I have here.
Yeah, we'll do this again. Either. Okay, so tell this here.
So connect to this Wi-Fi at the bottom, this Krishna LQR demo Wi-Fi, and then scan the QR code. You have to connect to the Wi-Fi and then scan the code, or else it won't work. No password. There's no password for the Wi-Fi. Actually. Is it scanning? No. Anyone try it? Did it work? Anyone try it? Did it not work at all? Anyone get it to Let's go to the No, you don't need internet or hotspot or anything. If you just connect to this Krishna LQR demo network, like just on your phone, you just click that network, then you can scan this QR code and that should work. Okay, if it doesn't work in the next 5 minutes, we'll move on. Oh, limit time. Okay, so if you press this run simulate button, the front digit. So you see how it balances? Then you can press it as the LQR, you can change it back up to that first second. So you turn off controlling. Okay, how about this? Actually, I'll just show it to you here, maybe.
Kalau dia suka kualifikasi datang
Okay. So, do you guys see the cart pull? So, right now, I'm able to click this run simulation button and it balances. See it? If I turn off the controller and I do it again, you see it falls down. Right? You can also change things. Right? So let's say it's so hard to see on here. That's okay. Maybe okay. Here's an example. Let's say I change the cost on the state to be 0. Now when I do this, you see how it balances somewhere else? Because I'm saying in the optimization problem, I don't care where the stick is. I only care that it's balanced. Make sense? Instead of that, let's say I make the stick balancing 0 and I increase the cost on the position. You see, it'll kind of balance, but it'll mostly actually. Oh, okay. Well, that broke the simulation. That's okay. But yeah, so you can play around with these parameters, figure out which ones break the simulation, which ones make it work. You can control the mass at the end of the pole and the mass of the cart. I'll link this at the end if you want to play around with it. Feel free to download it, run it yourself. But yeah, so I just wanted to show that I'm not just saying random math things, it will actually work when you implement it. Okay, let's go back to these. Okay, so this is kind of what it'll look like. If you, instead of just doing the linear dynamics about the top, if you allow the full nonlinear dynamics, now you're able to actually do the full swing up motion too, which is pretty complicated. But the problem is now the optimization problem is way more difficult to solve. And you can even extend it to more complicated systems. This is a triple pendulum. So it's 3 of these linked together. You can swing up, and then it can change where the top is. So just put 1 link down, 2 links down, all that stuff. So let me just talk a little bit about limitations, problems with what I just talked about. These tools are really powerful. So this is a rocket, SpaceX rocket, where they're able to control it to land it and catch the rocket before it explodes. This control system is really actually similar to what I just talked about today. It's closer than anything else. So you see how it's able to control the bottom thruster? And so it comes softly and land here. And while I would say that the control system and control techniques are important here, I would say the actual system engineering to make the rocket not explode before it even gets to that point is incredibly important and probably a much harder problem to solve in a lot of these systems. So even if your optimization problem is hard and you're able to solve it, the actual system engineering to actually make it work is incredibly hard as well. And in this setup, we ignored a bunch of the important parts of the dynamics. Like the gearbox in a motor has huge impacts on the performance of a system, right? Like there's incredible nonlinearities in how the gears are shaped, the expansion of the gears. There's like cogging torques, like crazy things. They're very important. And this problem that we talked about today is what's called a convex optimization problem. So it looks at this bowl, and you as a human, you can just look at this and be like, oh, the minimum is right there. And if you start anywhere on this bowl, like if you put a ball anywhere, it'll roll all the way downhill and be in the right place. Unfortunately, the real world is what's called non-convex. The optimization problem, that cost function, is not like a bowl. It'll be wavy, a bunch of random stuff. And there'll be a bunch of what are called local minima, places where you don't get the correct solution. Like that bottom point right there is the correct solution. But to actually get there is really difficult. So these system engineering problems and these modeling problems, these abstractions that we made, one way that we can kind of like solve and think about these problems is by using data of the real system. So we have some model that we just talked about, that like pendulum, rigid body model. Most of the stuff that you learn in mechanical engineering are models. And we have a real system, right? Like a real robot, a real car, a real engineering, or like a power plant, any of these things. And if we take our model and we do something and we run it on a real system, we can take the data that the real system generates and improve our model. This is called system identification, or model fitting, or real systems, or a bunch of names for it. Or instead of just using one model to design what our robot should do or whatever system should do, we can use a collection of models. So let's say that the weight at the end of the pendulum is unknown. Let's say it could be 5 kilograms or 10 kilograms, right? Instead of just picking a number and doing it, you can optimize over a bunch of different weights to create what's called a robust policy. So you can either make your actual controller robust, or you can take the real world data and improve your model, or you can do both. You can do all of these things. This is one project that I'm working on now. It's called a flying knot, where you take your hand and you tie a knot in a rope with just one hand. And then the question is, how can you teach a robot to do that? So in this system, instead of having a model which I'm optimizing, I actually just improve the real system directly. And if I can do that efficiently, then it only takes like 3-4 trials for it to learn how to do this task. So in this task, I give the demonstration, one demonstration of how to do it, and then it does a couple trials and learns how to do the task. Does that make sense?
Yes. Thanks.
And then if you give it a new rope, you can just do that same learning process on a thicker rope, a thinner rope, a stiffer rope. And some rope it doesn't really work too well. Yeah, like this rope right here is much, much thicker than the original. Okay, we have 5 minutes left. Overall, I'm going to just say that I just sent you all for a good amount of time. But I hope that you got at least something super useful out of it. If nothing else, I hope I showed you some cool robots. I think that robotics in general is really a systems problem, and as a mechanical engineer, really your job should be to understand deeply what models you're using and why you're using them, because when you actually apply these models, you can't just blindly throw stuff at the wall. You need to be more methodical, thoughtful about how you're actually applying the model and where the models will fail. Being super aware of that is what makes you a really good engineer. Let's see. Okay. I think that's all. I'm going to just end with some resources. This course at the top, this Optimal Controls course taught at CMU, is really, really good if you're interested in more of this stuff. All the lecture videos are online, all the homeworks, all of the assignments, or like the lecture notes and all that stuff. So if you're ever interested, please check it out. The link to the slides, QR code, feel free to take a picture. That's all public. And feel free to email me as well, anytime. And then all the code is on there. Sorry the demo didn't work that great, but hopefully you got something out of it. But yeah, that's all. Thank you for your time.